Good. Welcome back. Let's see. In the last classes, we have seen that if you want to study possible forms of dynamics on a statistical manifold on a simplex, and by dynamics I mean possible families of curves that fill the manifold, flows on the manifold, it is sort of natural to impose that a certain structure, the symplectic form, be conserved. So you set the derivative, the Lie derivative of the symplectic structure to 0. The corresponding flows are Hamiltonian flows. So that's how we get Hamilton's equations in physics. Very good. In order to do quantum mechanics, we need to impose additional structures. And so one of the things that we realized was that, well, the simplex already has a metric structure, but that's not enough because what we're really interested is in the phase space, the epistemic phase space. And so while there is a metric tensor for the simplex, we do not have a metric tensor for the full cotangent bundle. So the goal we set up for us in the last class was, well, extend the metric structure that we have for the simplex to the full cotangent bundle. And we got an expression. Assumptions were required. The crucial assumption that is being made in this is that we're going to preserve the spherical symmetry of the simplex into, or extend that spherical symmetry into the whole cotangent bundle. So we're imposing on our dynamics a certain spherical symmetry. Is this an ad hoc assumption? Where does this come from? Well, of course it is ad hoc. It is an assumption designed to work for quantum mechanics. If we were doing inferences about, say, the stock market, which is my paradigm example of something that's not physics, if we were trying to do inferences and dynamics for the stock market, you would not impose a spherical symmetry. Just like you might want to impose a cubic symmetry if you're dealing with perfectly nice cubic dice, right? That's the physical symmetry is that of a cube. You impose it on your inferences and you assign 1/6 to each face of the die, right? It makes complete sense to use physical information to match it to the probabilities that you're trying to compute. In exactly the same way, we're imposing a spherical symmetry on our inferences because eventually that will lead us to quantum mechanics. At some point in all of this, it's not just mathematics. You really have to impose physics. It is the spherical symmetry that introduces something that is of physical relevance. Very good. So let's proceed with this a little bit. I'm going to switch to my tablet so that then I can write down my equations. And so here is the metric that we had concocted for the cotangent bundle, which is here. Remember, the simplex is a simplex of n-1 dimensions. We enlarge it to the unrestricted space, one more dimension, so that the probabilities need not be normalized. And then we include the cotangent spaces in the bundle. And here we have the metric. So this looks like a pretty awful kind of expression until you learn to read various pieces of it. So let me make several comments about this metric, or the metric implied by this line element. The first remark is that if you're looking at what's going on when you are moving on a space of constant pi, namely you set delta pi equal to 0, i.e. the pi i's are kept fixed, then one reproduces the spherically symmetric metric of the space of non-normalized probabilities. And if we normalize the probabilities, we reproduce the metric of the simplex S. So, of course, then what this means is that if you set delta pi equal to 0, you just reproduce information geometry. Perfect. Nothing surprising here. We designed the metric in such a way that it will include, as a special case, the information geometry of the simplex. Perfect. Second remark. If this is supposed to describe a spherically symmetric space of 2n dimensions. In the spherically symmetric, in the particular case when the function a vanishes and the function b, with both of which depend on the normalization, right? And the function b is equal to a constant, which we can just set equal to 1, then the metric of this space is 2n dimensional, is the metric of a 2n dimensional flat Euclidean space. That's the simplest possible embedding space that you could come up with. One of the real purposes of having kept these functions a and b sort of arbitrary here is that we do not make the unnecessary assumption that the embedding space is going to be flat. It can be generically curved, spherically symmetric curved. Let me see, what else? Yes, the last, and I would say the really most important comment here is the following. The way we actually proceeded to identify what the metric for a spherically symmetric space was to use pseudo-coordinates, pseudo-Cartesian coordinates, and those were called eta, xi, and eta. And the way we identify this was we transformed to these pseudopolar coordinates. So we transform from xi eta to the coordinates, pseudopolar coordinates theta and pi. Eta I is theta I 1/2 sine pi I. Very good. So in these coordinates, it was in the xi eta coordinates, it was very clear that we derived that from, we were coming from a generic spherical space. When we make the transformation to identify where theta and its momentum are contained or are represented in this space, eventually we get to this formula that we have up here. But the particular transformation is very telling because it has two important implications here. The most important thing that we can immediately see is that the point theta and pi is the same as the point theta and pi I plus 2 pi. Do not confuse the momentum pi I, Greek pi here, Greek p, with pi that appears here, which is the 3.14159 blah blah blah, right? But in any case, if you change these pi's by 2 pi, you obtain the same xi and eta. In other words, one of the things that is becoming clear when we make this particular identification, when we say, okay, in those pseudo-Cartesian coordinates, the coordinates were xi and eta, but where is the momentum that is actually conjugate to the probabilities? We made assumptions to that, and we chose this form. Well, this choice is not at all innocent. It is telling you that the momentum pi I has the properties of an angle. You increase it by 2 pi and you do not change the physical situation. So therefore, the momenta, I'll write it in full glory, the momenta pi I conjugate to the probabilities which are the object of our attention, the object of our interest, are angles. Second, when we have the simplex, and the simplex is a funny curved space, let's write the embedding space, which is spherically symmetric, and at each point here we put a cotangent. So this is the point theta, and this is the space that is cotangent at the point theta. Well, cotangent and cotangent spaces are flat, granted, but what the first statement here is telling us is that if we take a particular point pi in this place and we add 2 pi to it, we are effectively identifying edges of this cube or square that differ by 2 pi. You have here a coordinate and here is the same coordinate pi plus 2 pi. These two are the same points. So the conclusion is that the cotangent plane space, cotangent space T star S plus 1 at the point theta, and in fact it's for all the cotangent spaces, are hypercubes. By cube, I mean basically a square which is flat in many dimensions, so it's a cube. Hyper because it's many dimensions, not 3, and there are hypercubes with opposite faces identified. It's like in these hypercubes you have periodic boundary conditions. So this is crucial. Both of these statements here are crucial for the statement of quantum mechanics. Of course, they are essentially equivalent. This is the kind of thing that tells you that wave functions are going to be single valued. Okay, so this is where those things come from. Very good. So those are two important comments on the coming from the particular form of the metric that we have identified here. Very good. Next topic. This was our step B. Step A consisted in taking the simplex and embedding it in a spherically symmetric S plus 1, removing the probability normalization constraint. The next step was to take that S plus 1 and extend its metric to the full cotangent bundle. That was step B, and that was accomplished here. Our third step is going to say, well, all right, it's nice, we have the metric for the full cotangent bundle, but really what we're interested is in T star S, not T star S plus 1. We want the phase space. So the next step then is the metric of the epistemic phase space T star S. Fortunately, this is relatively easy to do, and the reason ends up being typically if you have a larger space and you want to figure out the distance between 2 points, use the metric. If those 2 points happen to be contained within a surface, within a subspace, then the formula is exactly the same, just compute. So figuring out the induced metric on subspaces is typically very simple. There is one complication, however, which is the following. So we want the metric for between points that lie on the simplex this is the normalization condition, the sum of the probabilities. We would like to impose that is true. Okay, that's not so bad. This first part of the calculation is going to be very easy. If you just impose that the normalization is 1, then you just write A at the point 1, calculated for argument 1, and you write B at the point 1. Furthermore, because the sum of the probabilities is supposed to now be equal to 1, the normalization is 1, the sum of the deltas is going to be 0, so this whole term here disappears. So this implies that the metric of interest is going to be B of calculated at the argument 1, and then we just proceed and do our delta thetas. Theta I, we're summing here I equals 1 to n plus 2 delta I delta pi I squared, where of course there is a mild complication in the fact that these deltas are not completely independent. So if I tell you the deltas for the first n minus 1, you will have to figure out what the remaining one, delta n, is going to be, and you plug it in and you're in good shape. But there is another complication that's a more serious. And that complication is that the points theta pi and theta and pi plus a constant, so these are something like that, a constant nu. Remember, the constant nu is called a constant because it does not depend on the index I, right? Those are supposed to be equivalent. Okay, they lie on the same gauge orbit or the same ray. So how did that come about? Well, remember how this worked. The normalization can be a pain in the neck because it means that the probabilities are not all independent. So we tackle that by saying you enlarge the space to non-normalized probabilities and you treat them all independently. So that means you have an extra probability coordinate. But if you're going to have an extra probability coordinate, you're also going to have an extra momentum associated to it. And so how do we handle that one? We say that, well, points that differ by, the momentum differs by a constant are meant to be equivalent. They represent exactly the same physical situation. So they are in the same gauge orbit or the same ray. So when we say, let's see, when we say we want to figure out the distance, what do we mean? Do we mean the distance between the point theta and pi? So distance. We want to compute the distance between theta and pi and theta and the theta and theta, and pi plus d pi. Is that what we want to compute? It appears that this is what this formula is telling us. Or do we want to compute the distance between this guy and something that is equivalent to this? So what delta nu do we pick when we compute here? Should we compare the distance between, maybe I should just, let's set b, this b equals to 1. We don't need to worry about that one anymore. That amounts just to a choice of units. So this is all the way up to 1 squared theta I plus 2I, where for delta pi, we're going to have delta pi, the change in the pi's, up to any shift by a constant. So the question is, do we pick a distance with the delta nu equal to 0 or a distance between equivalent states? Basically what we're saying here is that if you're going to pick any point on an array, well, my motion here is a shift in the nu direction, or any other point in an array, it's okay. We're going to normalize this as far as probabilities goes, but that does not mean that we know what is the pi that you're going to put there. Which pi here corresponds to the pi on the other array? And we have to make that decision there. So what we're going to do is we're going to say, we're going to choose. So first, we impose that the delta thetas all add up to 0, right? So this means we're definitely going to look for points on rays that have exactly the same normalization for the probability. Very good. But furthermore, we're going to choose that delta here that makes the distance a minimum. So when you're trying to look for the distance between points on different rays, we're going to pick the point on the other ray in such a way that it is closest to the original one. So the distances on Ts, T star S plus 1 and T star S are different. Distances between rays require that you pick the 2 points that are closest. So we're going to impose that the true metric, let me call it ds squared, be the minimum of this delta L squared when you vary the point along the second ray. So what we have to do is we have to minimize this quantity here, So these points, let me see, I can clean up the notation a little bit more. We have specified that we are on the normalized simplex. So this is the metric on when you are on the simplex. So for that special case, let me introduce a special notation for this to distinguish it from the more general metric. And you have a tilde there, and you have a tilde there. That tilde just means probabilities add up to 1. Very good. So now let's figure out what that is. So what I want to do is I want to take the derivative of this delta s squared with respect to nu, and we're going to set, with respect to the change in nu, and we're going to set that equal to 0. The calculation is trivial. When we do the derivation of, it's better if I do it right. We're going to find the minimum of this when I vary over delta nu and see what is minimum, how is that minimum achieved. And when you do that, look here, the first derivative, the derivative of the first piece with respect to nu vanishes. So what we are going to have is the factor of 2 that comes from here, the sum over I up to n of theta I. Then we take the derivative of this guy here. It's a 2, which I write here as a 4. And then I have the delta pi I plus delta nu multiplied by the derivative of delta nu with respect to delta nu, which is 1. So this is it, and this is supposed to be equal to 0. So look at what we have here. The first term is the probabilities multiplying the changes in the momentum pi. So what this is just the expected value of the delta pi's. Plus, here we have, what do we have here? We have this constant, delta I, and this is just the sum of the probabilities, which is equal to 1. So what we have there is that delta nu is equal to 0. So the conclusion is that the delta nu that minimizes the distance between two rays is going to be minus the expected value of the delta pi's. So what I'm going to do now is find what the minimum of this delta L squared is by substituting the minimum, the delta nu that achieves that minimum here, and it's just going to be delta pi minus the expected value. So let me write it out explicitly. The metric on the epistemic phase space is given by, there is a constant, an overall constant, and then there is I equals 1 to n. There is the metric associated to the simplex, and then there is the metric associated to the cotangent spaces, and this is going to be delta pi I minus the expected value of the delta pi i's all squared, like so. Very good. This is the metric. We have it. So now we can start doing all sorts of physics. But before we proceed to do that, we see that this metric is sort of like complicated by this extra factor here. By the way, this metric is called the Fubini study metric. It was a metric that was discovered sort of independently by Fubini and this other guy who signed himself as Study. I don't know if it's an actual name or if this was just a pseudonym. And this was done in 1906, way before people were interested in quantum mechanics. Nevertheless, they were studying metrics in complex projective spaces, and they really wanted to figure out what happens when you are trying to figure out is not the distance between 2 points, but rather the distance between 2 rays. So what we have just derived is the Fubini study metric. Now we can write the metric from here. We can write a metric that applies to vectors. So suppose you have 2 vectors. Two vectors on V and U, then the scalar product of 2 vectors. We can imagine that these delta thetas and delta pi's are the coordinates of infinitesimal vectors. For vectors that are not infinitesimal, then the scalar product would look something like this. So we would have something like that, and then here we're going to have the components, the theta components of the 2 vectors. That corresponds to that first term, plus 2 theta I, and then here we will have the pi components of the 2 vectors. And now we finish. So you can see that this metric is still kind of messy. Now we can simplify this considerably once we realize that whenever we have a vector, because you have this symmetry that you can always shift the pi components, the momentum components, you're really dealing with equivalent vectors. But this can be simplified, and we're going to take full advantage of this by recalling a little. I made a very short comment at the end of a lecture a couple of times ago when we said that the vectors v prime and v are equivalent whenever the vectors v prime and v differ by a component along the direction of the vector n, which is the flow that's generated by the constraint. So remember what this guy had. This had one component, the probability, the components along the probability directions are 0, and the components along the momentum directions are 1. So whenever you have something that shifts the momenta components by constants, there is no I here on the right hand side, these two are equivalent. So what this allows us is, if all of these vectors are going to be equivalent, it may be to our advantage to pick a representative of this family of vectors. Choose a convenient representative of the family of vectors that are equivalent to V. In other words, V, the vector V, may be a mess, maybe something complicated to work with. Well, is there a V prime that would be better? Well, actually, yes, because we can choose, we can fix the gauge. This is what's called fixing the gauge. Fixing the gauge means in a family of equivalent representations, pick one. Pick the one you like best, one that's easier to play with. And what we're going to do is we're going to take the pi components, let me do this right. This is V prime. Take the pi components, alpha equals to 2, and we compute the expected value. You see the expected values are what appears here. So we say, look, whatever the expected value of V2 might be, we can always add, figure out another vector, V prime, that's equivalent to it, which is something like that. And so what we do here is we choose K. Oh, yes, okay. Before we do that, what is the expected value of N2? Expected value of N2 is going to be, because the N2I is equal to 1, this is just the expected value of theta, so this is 1. So what we're going to do is choose the K that makes life simplest, because this new representative has expected value of the pi components equal to 0. If we choose this particular gauge, then we can simplify the form of the Fubini study metric. Then the Fubini study metric is simplified. And what that means is the following. The condition that the thetas be 1, so that we have, let me write it differently. We want vectors tangent to the simplex. What that means is that the vectors are supposed to preserve this condition. In other words, if you take the components of the vectors and you add them, so that what we have is something like that, these components vanish. So for vectors tangent to S, the condition that we want is that the magnitude of the probability components, which is what I wrote here, be equal to 1. So therefore, for these guys, we want them to be tangent. This is the condition. But we also want to pick not just the theta components, we want to pick the pi components so that it simplifies life. Also then gauge fix the gauge, convenient gauge choice, we're going to impose that the vectors we consider are such that the expected value of their pi components is equal to 0. So the first condition, what the first condition says is that we're forcing, you are in the cotangent bundle plus 1. So this is too many dimensions, 2n. You want to eliminate two dimensions here. We eliminate one by forcing the vectors to generate motions that are tangent to the simplex. It remains to eliminate one of the pi components, one of the momentum components. We eliminate one of the momentum components by choosing that the momentum components satisfy this condition. So this reduces the number of dimensions from 2n to 2n minus 2. Very good. Then, so these are called vectors that are tangent and gauge fixed, TGF vectors. For these vectors, TGF vectors, the metric takes a simpler form, because we're going to have the metric here in which we have this first piece, yes, but then this expected value of V2 and expected value of U2 disappears. So for these vectors, for these specially TGF vectors, we have that the scalar product is given by I equals 1 to n 1 over 2 theta I v I u I plus 2 theta I v I sorry, let me do this right. I forgot. These are the theta components first. So this is going to be v1I u1I plus 2 theta I v2I u2I. Very good. So that's the metric for TGF vectors. This gives you the metric for the, really, it gives you the metric for the whole ray. But if you compute it further, but for the whole ray, it's going to be more complicated. It includes that additional piece. If you pick the TGF equivalent of those vectors, then you simplify it. For these vectors, we can actually write the following. If we write of course, we can also write the line element in exactly the same way. 1 over 2 theta I delta theta I squared plus 2 theta I delta pi I squared, where it is assumed here that the little vector delta theta I delta pi I is, of course, TGF, which means that the delta theta i's add up to 0, and the expected value of these delta pi i's actually is equal to 0. Very good. So we have a metric there. We can actually go ahead and write what the metric components are going to be. If we write the metric in terms of components as follows, we write the element as being, well, we have alpha I, beta j, and this is the delta x, alpha I, delta x, beta j. And I remind you, this delta x alpha I is just delta theta I and delta pi I. Okay, so if we write this like this, and we look up what these guys mean, then the conclusion is that the metric takes the following, the metric tensor takes the following simple form. This guy here is going to be, I'm going to write this as a form of a 2 by 2 matrix with alpha and beta being the 2 by 2 elements, and it's going to be delta ij and then divided by 2 delta I, delta ij multiplied by ij, and then zeros here. So the metric is diagonal in alpha and beta, which of course you can see from here. You can see it from here. There is no delta theta, delta pi terms. They're diagonal. Very good. So we did it. Okay, this is the metric. Okay. Remark. This is the metric. This tensor. This tensor, caution, right? This tensor can be applied to any vectors. That's what tensors allow you to do. You can apply this tensor to any vectors. It is the metric only when applied to TGF vectors. So I hope you see that there is that technicality that we were discussing for a while now, that the probabilities are normalized, comes back to bite you at every step of these calculations. You have to really make sure you understand what you're doing with this normalization. It seems trivial. Of course, probabilities are normalized. Yeah, it is trivial. But technically, when you want to keep track of what the implications are, it adds up. It adds a lot of the formalism. But basically, it's not complicated. It's just that you have to introduce one more coordinate in order to be able to keep track of the spherical symmetries in a more or less explicit way. And if you introduce one more coordinate, you have to introduce another momentum. And then at some point say, well, I don't care about those extra additions. I have to get rid of them. So here we did it. We got rid of them. Very good. So now I'm going to tell you something kind of remarkable. Because the moment that you have a tensor and you have another tensor, we could, for example, take G and compute its inverse. So let me do it by like that. Having a metric, we can compute the inverse. It turns out that the inverse of this tensor that we have up here, because it is diagonal, is very simple. You just invert these guys here, 2i delta ij, and then this is going to be delta ij divided by 2 theta I. So taking the inverse is very simple. But now that we have this guy here, nothing prevents us from using it to raise and lower indices of other things, including, let me do this guy here, gamma k, and now what I wrote here is the symplectic form, which is another tensor that has two indices downstairs, and beta j. I'm summing over gammas and I'm summing over k's. So whatever results from this manipulation is going to be a tensor, and this tensor is going to have an index upstairs and it's going to have an index downstairs. So this is a mixed tensor. So this is a 2, 0 tensor, this is a 0, 2 tensor, and this is a 1, 1 tensor. It's mixed. When this object here acts on vectors, it contracts the lower index with the upper index of the vector, it produces another vector. So this is a tensor that maps vectors to vectors, maps vectors to vectors. This guy here, on the other hand, maps vectors to covectors. This one here maps covectors to covectors. The metric tensor itself maps vectors to covectors, just like the symplectic form. Now, this object that we have just defined here has really interesting properties. We just defined it this way, right? It's going to turn out to be convenient to introduce a minus sign, and we're going to define this tensor, mixed tensor J in this particular way. You see that I'm not doing anything questionable here. If I give you a tensor, you can figure out the inverse. And if you have two tensors, you can always contract them and find a third one. It turns out that without any additional assumptions, once we have a metric tensor and we have a symplectic tensor, we can always do this. The tensor J is very interesting because if you do the contraction of the metric tensor with itself, you take the square, you see, I just took the metric tensor and contracted the second with the first index. When you do that, what you get is minus the identity tensor. In other words, if you take the vector v and you apply this tensor j, and then you apply the tensor j again, you get minus the original vector. What this means is that there is a structure in this space. Once we have the symplectic structure and the metric structure, there is a structure here which resembles complex numbers. There are no i's anywhere on site. There is no square root of -1, although there is a square root of the -1 minus identity matrix. There is no square root of -1 at this point. But there is an object that plays exactly the same role. If you multiply by I and multiply by I, you get minus V. So what we say here is that J provides a complex structure. We have a symplectic structure and we have a metric structure, and when the metric tensors take this particular form, then there is also a complex structure. This is why complex numbers appear in quantum mechanics. It is a consequence of having a symplectic structure and a metric structure that is spherically symmetric. This is how complex numbers emerge in quantum mechanics. This is how complex numbers are introduced into quantum mechanics. Very good. Time to stop here. What we're going to do in the second half of this lecture is exploit this idea a little bit further. See you then.